Okay, good. So, yeah. So let's recall what we proved yesterday. So recall. First of all, we called the GUE matrix. So this was an n by n matrix, Aij, such that these Aijs are independent, standard, normal. Of course, in general, complex, self-adjoint or Hermitian matrices, right? Yeah. Okay, and then what we proved yesterday was that, so we proved this topological expansion. Which basically said that 1 over n expectation value of trace of an over root n, the power 2n. This converges to, as n goes to infinity, the nth Catalan number, which is equal to the nth moment of Wigner semicircular distribution. Wigner distribution. And we interpreted this as a version of, we said actually, that this is a version of Wigner semicircular law. So let me now put it, this is the weakest form of Wigner semicircular law. And I will tell you in what sense this is the weakest form and how people gradually generalized, I mean, not generalized, actually strengthened this version, semicircular law. Okay, by the way we proved this was, this is not topological expansion. The topological expansion is that this expression is equal to, we proved actually, is equal to 1 over n to the power n plus 1 sum of we got the expression n to the power n plus 1 minus 2g. Yes, g bigger than or equal to 0. And then there were some coefficients here. So these coefficients, I'm not sure what name I gave them, but I'm going to call them epsilon gn. It depends on g, which is a running index. These coefficients are totally independent of n, and of capital N, I mean. So this is little g, and that's little n, and that's. And so basically, the way we prove this statement by showing, first of all, this expression holds, and also the fact that epsilon 0n is equal to Cn, is the nth Catalan number. Okay, is that clear? That's how we proved. So we proved more than actually this. In other words, we just proved this beautiful topological expansion, which brings in the theory of surfaces, which has a very, very deep connections to Riemann surface theory, to topology, to quantum, two-dimensional quantum gravity, to a lot of things. But for now, it's just like a combinatorial device. We don't see its deeper meanings yet. Okay, so that's the way we prove it. By the way, let me make a comment here. Sometimes you may find yourself, someone is saying that actually Wigner's semicircle law is 1 over n, expectation value of trace of an over root n, not over root n, you just put an to the power 2n. They don't normalize, converges to Cn. Of course, in this case, these AIJs are standard, they are not standard normal. They are like, they have mean 0, but the variance is 1 over n in that case, right? In this case, the variance of an is equal to, it's got to be equal to 1 over n. So in this case, the variance is 1. I mean, sorry, Aij, I should put. In this case, the variance of Aij is 1 because these are complex standard normal, but in this case, it's 1 over n. So you may see both versions, so be aware of this complication in notation. Okay. Is that clear? No, are there any questions? I mean. Okay, now I want to indicate in what sense this is the weakest form and how we can possibly extend this to, and not extend, strengthen this into to a maybe deeper version. So let's see. So we have to look at this matrix ensemble. So GUE ensemble. So it's a probability space Hn, which is n by n Hermitian matrices. And then there is a probability measure on that space. So which total measure 1, of course, total probability has to be 1. And that one is given by, given in 2 forms. Usually you see it in 2 forms. Either you see it as d mu of h equal to 1 over z, some normalization, exponential of minus 1/2 trace of h squared. Okay. If you see it this way, then this means that, so here is an exercise in this case, or you see it in the following way, d mu of h equal to 1 over z. Now, this is a different z. This is a different z. This is a different normalization. Exponential of minus n over 2 raised of h2. And you might wonder which one is the right one. Well, if you choose, so here's an exercise. In the second case, these AIJs have variance 1 over n. So in this case, if you want to write if you want to write those limits, you should not divide by root n. But in the first case, all AIJs are a standard complex normal. Variance of AIJ is 1. Okay, so this is case 1. So these are kind of annoying features of notation, which is sometimes actually confuses us. I mean, so I'm just giving you some indication that be aware of these things. And if you try to solve these two questions, you will be served well. Okay, anyhow, so with this or that, we have this probability measure. Now, then what we have is the following. For any a Hermitian matrix, we get a probability, so let me put it this way. You do get a discrete probability measure on R. So imagine I'm using 2 now. So I want to use this version 2. So I'm going to put this probability measure on Hn, not this one. So I use this one. So you get this, then this measure mu A is the following. 1 over n sum delta lambda I from 1 to n. So this is the atomic measure, the Dirac atomic measure or Dirac mass. I mean, when you take these courses in measure theory, you know that you can define these sort of discrete measures on any space. Well, yeah, you define sigma algebra, you define measures. So this basically, yeah, so Dirac mass supported at eigenvalue lambda I. So basically, what happens is that you just you put these eigenvalues on the line. I mean, some of them may coincide, it doesn't matter. And then basically, each eigenvalue has mass 1 over n. So the total mass is, but the thing is they can occur in any point. So, yeah. So this is a measure, this is a probability measure. This is a probability measure, right? So this map A to mu A that goes from Hn n by n Hermitian matrices with this probability measure to, it goes from Hn to where? To the space of probability measures on R, right? Probability measures on R. So this association of A to mu A is a random variable, but it's a very sophisticated random variable. It's a probability valued random variable. In other words, for each point in the sample space Hn, which means each matrix, you attach a probability measure, discrete probability measure. So, okay, but we have infinitely many matrices, and this is a random object, very sophisticated random object. Now, what we can do with this random object, so basically now, the point of Wigner's semicircular law is that it is the sequence of random variables in this sense that converges to the Wigner semicircle distribution. Now, all these things have to be interpreted correctly, and we have to define what we mean by all these terms. So basically now we have this object which is much more sophisticated than those numbers, expectation values now. So a kind of Wigner semicircle law. So this is a kind of meta version, if you want. It's a meta version. It means it's not completely true, but it's a general idea of what we expect to be true. Meta version is that this mu A, I mean, we have to put some n here also, because it depends on n, right? Converges to this mu Wigner semicircle. Now, if you look at this statement, that's a kind of tall order here to establish this, because first of all, these mu ANs, they go from different probability spaces. They go from Hn. And this, you have H1, H2, H3, H4, and all of them. They are all very different. So we have a sequence of random variables from different probability spaces. And they go into same thing here. So goes to this target space, which is, I just put probabilities on R. Just like that. Okay, and then what about this guy? This guy is an element of probability space R, okay? But we can think of it also as a random variable, but it's a deterministic random variable. It's a random variable that's constant. It's just one probability measure among all possible probability measures, okay? So now we have to see in what sense these sequences of probability measures, random variables, converges to this deterministic random variable. So this is deterministic. And so it's not necessary for us to get into all the details of the meaning of this convergence, but I just tell you that in probability theory, when you have a sequence of random variables, there are actually different notions of convergence of random variables. And I can tell you maybe one of them out of 3-4 types. So let me just tell you one, maybe two, actually. So here's the definition. So we are going to be very general now. Let omega n and Pn, and from 1 to infinity, be a sequence of probability spaces. And let now I just say xn from omega n to y be a random variable where y is just a space with a sigma algebra. These are called measurable spaces. So that's a bit abstract. I'm sorry, but I want you to be aware of some of these issues. But measurable, y is a measurable space, right? And let x from omega to y be another random variable. So now the first kind of convergence we can imagine, we say xn converges to x almost surely. So this is almost surely. If now, if xn of omega n converges to converges to okay, so there is this guy which I don't know what to make of it because there is this limit. I want this to converge. It's a bit problematic to define what does this mean in this generality now. Yeah. Okay, so okay, so now, okay, so this is a so I just say which is deterministic. Deterministic means that the value of x is actually almost surely independent of any omega you choose here. It's basically constant. Like you just choose one probability distribution, which is Wigner semicircle there. Let me say this converges to x of omega 0 for almost all with probability 1. Let me put it this way, with probability 1. Okay, so what does this mean really? So this is, imagine, this is omega 1, this is omega 2, this is omega 3, and so on. So this is x1, this is x2, and this is x3, and so on. So basically, we are saying that for almost all points here, except a set of measure 0, almost all points here, except a set of measure 0, almost all points here, except a set of measure 0, this limit exists. and converges as a probability measure to this constant probability measure. So I don't bother to write it because there are many, many details I have to put down on the, but because it's not very essential for us now. It's just, I will give you a reference later on if you want to study this very carefully. So what does this mean? It means that if we just, this sequence of probability measures is going to converge almost surely to that constant probability measures. But we have other options. We can take the average value of each of them, or expectation value, and this would be convergence in mean or convergence in expectation. And this is honestly the weakest type of expectation, because imagine you have a sequence of probability measures and you're just saying that the mean or averages of these things converges to the average of the other one at the end of the limit. I mean, this is a very weak, if a sequence of random variables, only the averages converge. Okay, this is something, but it's very, very weak. So let me put it the second type of, so this is convergence almost surely, but now I just say convergence in mean. So it basically means that the mean of these probability measures that we define here converges to the mean of this guy, of the semicircle. Now, okay, so what do I mean by the mean here? I mean this expectation value of this, what do I mean here? So this guy, you see mu n, it was a map from Hn to these probability measures on R. So sends A to 1 over n sum delta of lambda I. So each of the values of these things is a very discrete probability measure. They all have a height of 1 over n. It's just a discrete probability measure. But then you average, you can actually show, and that's not very easy, but it is true that when you average this guy is going to look like this, basically. So this is the mean. Now, the mean of this random variable, I don't mean the mean of Wigner semicircle distribution. I mean the mean of the random variable, which was deterministic and defines this. So this is really, I mean, I should put here this one, and this really is mean of semicircle. So basically what we are saying now is that if you compute these curves for each n, and then these curves in some sense converges to this curve. As n goes to infinity. So I totally agree. This is a complicated concept, and you have to sort of absorb a lot of abstract probability theory notions and spaces to come to terms with this. Maybe you have a question?
Oh, yeah. Oh,
you can go ahead. You can go ahead.
Okay, thanks, Andre. So on the top left there, is that the mean, or is that referring to the function that we constructed earlier? Like that mu.
This one? Which one? Here,
On the left side. Yeah.
mu n.
Yeah. Is
Yeah.
that the function we constructed earlier or the mean?
Depends what you mean by function. You see, this is a random variable, mu n.
Oh,
Mu
I'm talking about we constructed the function from HN's the probability measures on our
h n. You mean which function we constructed? This one?
the one that sends A to the sum of the Dirac measures.
Oh, yeah, yeah. This is this random variable. Yeah.
Oh, okay. Yeah.
Yeah, but this random variable is not anything like you have seen in life so far, I'm pretty sure. Because the random variables that you work with are just real valued random variables or complex valued. But this is a probability valued random variable. That shows the power of measure theory, actually, because it allows us to absorb these complex situations, actually. So this is a credit to the language, the power of language of probability theory. I mean, it's just the random variables. Most people think is just real or complex value. No, I mean they can take value in anything. You can have manifold random valued random variables. Then you can talk about theory of random manifolds, which is beautiful theory. I mean, and all these things. Is that clear?
Yeah. So what we're doing on the left side, on the top left side, is like we're taking the mean of this strange random variable.
Yeah.
Okay. Yeah.
We're taking the mean, and the reason we can take the mean is that we can do basically a lot of things in this space, probability of R, which we are not able to do in abstract measure spaces. For example, we can take convex combinations here and things like that. So this allows us to define integration of this sort of, because I mean, in measure theory, indeed, it's you define integrals of functions from general measure spaces into R or C. You cannot define into any general measure space functions like that. But if the image is a vector space or a affine space, things like that, you can still define theory of integrations. You can go through that and then, yeah. So this was a, yeah. So any other questions? Or?
Yes, I had a question. This was going back to almost surely convergent random variables.
Yes.
We
Yes.
started with a sequence of probability spaces.
Yes. HNs. Yeah.
Yes. But then we talked about convergence of the random variable at each point in the probability space.
Yeah.
But because the probability spaces themselves change, we
Yes.
don't have the same point in all of them, right?
Exactly.
So I guess in order for this definition to be really like rigorous, we would kind of have to have one probability space which we're working on, right?
Yes. You can do it that way too. What I emphasize is that what we have here actually makes sense. I can elaborate on that. But we can actually define one probability space out of these things. Namely, I think we can just take union of these things. Do we have to take union or Cartesian products? Okay, first, okay, so maybe we can define one big probability space and take care of that by that method you're suggesting, Andre. But now let me just defend this. Let me make sure to convince you that this definition also makes sense. Okay? So let me just tell you why this definition makes sense. Well, this definition makes sense because it just says anything you choose here and anything you choose here and then look at the limit, it's converging, except for you should not touch some bad points here, which has measure 0. And here also some bad points that have measure 0 and some bad points which have, if you stay away from those measure 0 things, this sequence, which is now indexed by n, nothing else, because omega 1, little omega 1, little omega 2, little omega 3 are chosen, right? And it converges. Does it make sense to you, this definition?
It almost makes sense. I'm gonna spend more time on it myself, and then it's all gonna be.
Yeah. So this is the one. So you see, what we do, I want to talk about limit of these guys. What I'm saying is that you choose your omega n any which way, little omega n, any which way you want from omega n, capital omega n. Except stay away from the bad part, which has measure 0.
But I guess I'm confused still, because we in order for us to fix our omega n, we need to have a specific choice of capital N, because otherwise it's not gonna be in that probability space.
This is omega n. I'm sorry, this is omega n. Sorry.
Okay.
Yeah. So choose omega n here, except you cannot choose from some bad points here. With a full measure subset, which has probability 1, you can choose anything. Now you see that this is a very, very strong result. I want you to compare with law of large numbers. Maybe you have seen the strong form of law of large numbers. Law of large numbers, the strong form, it's about almost sure. But in fact, that's formulation is easier to understand because there is one probability space and all the random variables coming from that probability space into R, and you average and you say that it converges almost surely to that. So that's still an easier, but has the same flavor of law of large numbers in this case. But I don't see logically to have a problem. I'm not saying this is necessarily true, by the way. I think it is true, but so a place where you can read up these things very well is the Terence Tao notes. This is basically his notes on probability and random matrices, I guess. He gives a very good discussion of different notions of convergence of probability measures that are appropriate for random matrix theory and the necessary probability theory that's there. So, of course, there are many other references, but that's. But again, I mean, it's not. 100% necessary for us right now, but it's important to be very clear about it. That it's important to know, what we don't know, what we understand, what we don't understand, really.
So Masood, in the definition that you gave for the almost surely convergence,
almost sure,
almost surely convergence, yeah, the one that Andre was just talking about.
Okay.
You made the random variables have values in a measurable space. Why?
You mean,
right?
Yeah, why? Yes.
So then how does this limit work with the y? Because this limit is values in y, converging to
Yes.
another value in y.
Yes.
But
So
it needs
how
to
does
be
this
a
limit work?
needs to be a metric space of sorts, right?
Yeah, you need a topology there, and there is a topology in the space of probability measures. You mean in this space, right? What is the topology here?
Well, that's a good question, but I was talking about the more abstract definition that we gave of almost surely convergence. I mean,
Oh,
we can change the definition to be a topological space.
yeah, you mean, yeah, so that Y indeed has to be some sort of topological space so that we can say what limit means. Just having a measure space indeed is not enough, yes.
I mean, we could make it like a Borel space, that we could make that be the measure.
Yeah, exactly. We can start with topological space and take the Borelians as induced by open sets and all that. Yeah, that's possible. Metric would be very good, and there are a lot of things here. So it's yeah, it's yeah. So this is just maybe I wanted to just quickly maybe bring your attention that there are these issues of what sense Wigner's and so to have a good discussion, we should go back a little bit and start with convergence of probability, a convergence of random variables, and even revisit the notion of random variable a little bit and brush up a little bit more abstract, more kind of borderline undergraduate, graduate level probability theory, because I understand in undergrad probability theory, most cases, they don't go into abstract things like that. Yeah, but you
Well,
have done some probability theory and measure theory anyhow, which is
I've done measure theory and I've been reading up independently on probability theory.
yeah, that's
And I
very
haven't gotten to law of large numbers yet, but I've just reached that section. So, I mean, by the time the project starts, I should have finished
that's wonderful.
the
Yeah,
chapter.
yeah.
And I'm
So,
pretty sure Andre has taken probability theory already. So,
Andre, you have taken good probability theory, right?
Yes, I have. And measure theory as well.
Oh, great. Yeah, yeah. That's so maybe I will discuss law of large numbers quickly in two versions, and just as a reminder, and maybe, but this is far more sophisticated than that because the setting is more complicated, honestly. But I'll tell you what law of large numbers is. Okay, so that's a good starting point, actually. Yeah. So law of large numbers. So in that case, we have one probability space. So this means just omega is a non-empty set, F is a sigma algebra, and P is a probability measure on the sigma algebra. Let Xn from omega to R n equal to 1, 2, 3, B, IID sequence. IID means independent, identically distributed sequence of random variables. Right? So these are IID sequence of random variables. Okay, so basically means each xn is a measurable function from omega to R, and all of them have the same distribution. I hope, no, I should not define what do I mean by the distribution here, or that's okay, I can define it. Should I define the distribution of a probability of a random variable? Okay,
Not necessary.
okay, that's okay. So then there are at least two versions of law of large numbers. One is the weak form, weak law of large numbers. The other one is strong form of law of large numbers. Then, so this is the weak law of large numbers. So then it says that xn, so let me put it this way then. Basically, xn converges to mu in probability. Where mu is equal to expectation value of xn. Okay, because all of them are equally distributed, so I can just take expectation value of any of them, which are equal. So mu is the mean. So basically, this in the weak form, it says that xn converges to this constant number mu in probability. But what does this mean now in probability?
I think we should have the mean of them, right? The mean of the first n.
Oh, I'm sorry. Yes, of course. X1 plus X2, yeah, thank you. Plus Xn divided by n, yes. As n goes to infinity, converges to this, yes. Oh, gosh, yeah. Good. So what does this mean in probability? It means that for any epsilon positive, the probability of absolute value of x1 plus x2 plus xn over n minus mu is bigger than epsilon, this goes to 0 as n goes to infinity. So this basically says that the probability or the measure of the set of points where this difference, the empirical mean, is more than epsilon away from its measure, from its mean, then this goes to 0 as. This is the weak, is called the weak law of large numbers. This was proved in for some special case for Bernoulli random variables. As I said, I mean, not in the most general case that we are writing here. Bernoulli did it only for Bernoulli random variables, the 0, 1 or 1 or minus 1 random variables. In 1700, around that time. And in one of the first, most important books in probability theory, which was written for the first time by Dan, was the book that he wrote called Ars Conjectandi, means that art of conjecturing. And he gives this and goes pages after pages after pages of computations, eventually proves this. And he says that I spent 20 years in proving this result. It's and even formulating it was not obvious because this is not the kind of convergence that any analyst or like Newton, Leibniz, Euler would consider. This is a very different, strange type of convergence. This convergence in probability in this sense. Okay, so this is part of the story. But now, what is the strong form of law of large numbers? The strong form, law of large numbers, LLN, it just says that this sequence of random variables, the mean, converges to mu almost surely. Means that for the set of all omegas here belonging to omega, except for a set of measures 0 in capital Omega, this mean converges to constant mu. This is the strong law of large numbers. This was proved, guess when? In 1900. Certainly bigger than equal to 1900 year. This was more or less proved by Borel. I mean, the reason that it took so long is that they didn't have even the tools to formulate it properly. I mean, they needed the language of measure theory and these abstract settings and these things. And by the way, its proof is much more complicated than this because in 19th century, there was a proof of this which was discovered by Russians, Chebyshev. Chebyshev gave a proof using Chebyshev inequality, which we all learn is the part of the tool bag of any undergraduate. Chebyshev inequality, Markov inequality, even, yeah, these two inequalities certainly are the first things you must know in order to do anything in probability theory. So I highly recommend you prove this using Chebyshev yourself. So proof using Chebyshev. Inequality. But this is far more complicated result. This is far more complicated. Okay, so you see, it's what is quite surprising here. Another one of the things that's very surprising is that this is converging to a constant. I mean, just yeah. Anyhow, so I mean, what we are doing, in a way, it's in the same vein, same flavor, but far more complicated. Far more. The setting is more complicated in a way. I mean, certainly we cannot just use law of large numbers to prove this Wigner semicircle law. If that would be the case, we wouldn't need all that combinatorial arguments about surfaces, all that things, genus expansion, all that things wouldn't need. So this discussion is just the beginning of a long story, beautiful story, but we don't want to go into that. Just be aware of this, and maybe we visit this at one point again, but I'm not sure. But now I'm going to go to, because we have some time still, maybe 10, 15 minutes. I want to actually go beyond GUE and see what we want to do actually in this project. But I really do recommend you think about it and let me know your thinking. And maybe there are other formulations of this thing. So we just talked about two types of convergence so far. Convergence in probability, almost sure convergence, but there are other types of convergence. There are other types of convergence of random variables and convergence of measures or probability measures. So all of them, they are GUE. There are a lot of different types. Yeah. Okay. Now, so this is I formulated beyond GUE, Gaussian unitary ensemble. So now we want to consider a different probability measures. So the measure d mu h, consider the probability measure d mu h equal to, again, I just write it like this, 1 over z integral. So it's not the integral, exponential of minus n raised of v of h, where v of h is equal to 1/2 raised of h squared plus something like g over 4 raised of h4. So basically, this part should always be there. This is not negotiable for us. It's always there. And this part is this potential added. Okay. So it's a good idea actually for now. I mean, this v is a polynomial in h for now, but it's a good idea for now. Just think about trace of h4, that part. Okay. Now, what is z? Z, of course, is the total integral, right? So it's just integral over hn is normalization minus n trace of v of h, which is trace of 1/2 h squared plus g over 4 h4, right? dh. So now the first question is this a convergent integral or not? That's a legit question, right? Is it convergent? Okay. What do you think? Is it convergent?
Probably, because otherwise we probably wouldn't consider it.
That's right. Exactly. We wouldn't consider. I mean, okay, so about that, we will come back to that, and then we'll see that there is good reason to consider non-convergent integrals also. But yeah, but that's a good way to think about it for now. Yes. In fact, this is convergent. Let us look at the simplest case, just the one-dimensional case. It's convergent. Okay, so n equal to 1. So we are dealing with the following integral over R, because this is space H1 is just R, real numbers, exponential of minus 1/2, right? X squared minus g x4 over 4 dx. And of course, this is convergent for g bigger than or equal to 0, right? So yeah, it's kind of clear that if g is negative, then this is going to explode at infinity. So this is not bounded at infinity. So this is going to go to explode. So this is not convergent. So this guy is not convergent for g negative. So this is okay, but for g less than 0, divergent. Okay, that. And now, if we look at this guy as to why is it convergent in general, let's look at it. See how we can prove that this is convergent in general now. right? So to prove convergence in general, it's enough to show that trace of H4 is positive and it's not negative, basically. So suffices to show trace of H4 is bigger than or equal to 0 for all H belonging to Hn. I mean, is that clear? That's because this is a negative number and this is the convergent part, so that's going to do it, right? And why that? How do you prove that trace of H4 is not negative?
Well, it's going to be the sum of lambda I to the 4, where the lambda i's are the eigenvalues of H,
Yes.
and all of them are real.
Exactly. So this is, yeah, indeed. Yeah. So this is even better than what I was thinking. I was thinking of constructing something, but this is, yeah, exactly. This is sum of lambda I to the 4, I from 1 to 4. No, n. Oh my God. And these lambda i's indeed are real. So these are like real number to power 4, non-negative number, and so that's it. Yes. So this integral is convergent for this now. Okay, so certainly we have a probability measure on this space. And now we want to play the same game. We want to find the large and limit probability distribution of this sequence of probability measures now. So the goal, so one goal is understand these limits of n goes to infinity, expectation value of trace of basically HNs I think goes to infinity is equal to 1. And also understand and see if these probability measures mu a by definition 1 over n sum delta lambda I converges to some probability measure on R. Now, so if this converges, this sequence converges, this would be moments of this probability measure, strange probability measure. So, and this question now is far more complicated to answer, far more than Wigner. And what happens is that in the limit, actually, mu is going to look like some deformation of Wigner. So imagine here G is positive. It's not going to be Wigner, but it's going to be some deformation of Wigner. And the goal is to find the equation of this curve, of this limit. That's one thing. And then something strange also happens, something else. Namely, for when value of G, when G passes or crosses some threshold value, after that, there is going to be phase transition. So this is going to decompose into two pieces. And for G very large, so basically for G bigger than GC, some critical value, this is going to decompose into two pieces. And finding and proving the existence of this thing and possibly finding its value is one of the reasons we want to study these things. And physicists are interested in this, and yeah, people in quantum gravity and a lot of things, a lot of yeah, probability theory and all. So it's related. So these sort of questions are related to a lot of things, and we want to look at to see how to prove existence of such limit distributions. And maybe if there is a way. So now, we may not be able to completely solve this in closed forms, but even getting some numerical handle on these things or some understanding of these things using different techniques is our goal. So yeah, I think for now it's enough. We stop, but tomorrow, if not tomorrow, I have to see my schedule yet. If not tomorrow, certainly on Monday, we'll start discussing some new methods of handling this. And I think after 1 or 2 lectures, we can discuss actually the problem, because there are many methods to go about it, but bootstrapping is one of the methods. And the model that we are looking at is a particular kind of model. So we want to apply the bootstrap technique to that model. So yeah, so yeah, this random matrix theory stuff is quite huge. I mean, like just there are so many different things, and just we have to just find a kind of niche area for ourselves to work on that for now. Hopefully to get a paper by the end of the project, so that you guys can prove that you have done something that's that was valuable. So that's the idea. Yeah. Any questions or comments? Yeah, basically, I mean, the idea of introducing these terms is that without these terms, it's called free theory. So this is the language of physics. When there is no force, so in classical mechanics, we say that particles move on straight lines with constant velocity. So when there are no forces. And this is a free theory. But when you introduce a force field, then Newton's equations become much more complicated to solve. And in general, you cannot solve those equations. And that's very similar to this. When you introduce this term, it means you're introducing interactions into the system. There's some force, there's some interaction. And that always complicates things. And as a result, the set of cases that you can exactly solve, they are called integrable. The case of integrable models are very, very rare, in fact. Yeah. Okay. Everything else is okay? Okay, I will send. Oh, by the way, this paper of Ettinghoff that I sent you, if you look at that thing, he actually tries to solve one of these models. I mean, this quartic matrix ensemble. He actually solves it. There's a little bit of glitch at one point in his argument, but his argument is essentially correct, and maybe I will review that as well. Another thing I wanted to do before moving to this was to give this Harrer-Zagier formula, because we wrote down this topological expansion And then there is some sort of formula for these numbers, epsilon GNs, the number of Riemann surfaces that you obtain of genus G by gluing a two-and gone. How many Riemann surfaces of genus G you obtain? It's given by this, and there's a formula for that, which when you look at it, you'll be amazed why this formula should be even correct. And to prove that, there is a method called orthogonal polynomials. And these orthogonal polynomials are in general very useful for many, many things, including random matrix theory. Actually, I can maybe recall that if we meet tomorrow, maybe I'll recall that too. Okay. So have a good day, and I see you tomorrow. If not, on Monday, then hopefully, yeah.
Sounds
Sure.
good.
Thank you. Bye.
See you
Goodbye.
soon.
Thank you. Bye.